developing next-generation research and technology, facilitating connections between AFRL industry and academia, unlocking innovation through a culture of collaboration. This is the AFRL Regional Network Midwest.
The Air Force and the Space Force are interested in minimally invasive wearable sensors. Having these sensors that could detect biomolecules or other biomarkers of health and performance could help to increase the performance and monitor the health of these airmen and guardians when they are on a mission. So microneedles are tiny microneedles that are about 1 millimeter in height and anywhere from 200 to 300 microns in diameter at the base to even a millimeter diameter at the base. So microneedles come in many different forms. There are microneedles that dissolve to deliver drugs. There are microneedles that can absorb analytes for offline analysis. And the microneedles that AFRL is currently interested in are conductive microneedles that will be functionalized with an electrochemical sensor. And they will actually send signals back to the electronics to measure analytes in the human. There are very few microneedle devices that are commercially available right now. The whole process of fabricating the microneedles can take some time, actually days to weeks. So our approach to addressing this problem of the microneedle packages has been to use fused filament fabrication. That was a patented technology until 2009, at which point, when those patents expired, a lot of consumer-level companies came in and started making printers. Along with the development of these consumer-level printers came open-source slicing programs, and some of these printers come with open-source firmware. So we're writing our own software program to get the microneedle shape that we want using this hardware. More specific context is that this is the microneedles I made in Dr. Tilley's lab in summer 2023 using their mold and UV curable resin technique. And electrochemical sensors normally require a working electrode, a counter electrode, and a reference electrode, and this was working to make those 3 electrodes. Here's initial attempts at drawing lithography, and you can see very irregular patterns in a lot of these. And this was the first microneedle device, which you can see that the microneedles are actually very far apart and not very uniform. And here you can see microneedles produced in my lab in the first period of performance. Here they're tightly spaced, only 1.25 millimeters apart. And one discovery or invention that has come out from this period of performance in the funding, we were refining our 3D printer-based drawing lithography. But we actually invented a complementary process called Continuously Variable Stacked Extrusion. And this actually deals with a positive phase of extruded material that bulges out beyond the inner diameter of the nozzle, whereas drawing lithography works in the negative phase. So we use these two together to get more complex shapes. And just as an example what more complex shapes can do, this is a group that used a process similar to drawing lithography where they draw via centrifugation, and they have 2 phases with a secondary dispensing phase, and they have these tissue interlocking shapes that will basically hold the microneedles into the tissue. And that's something we should be able to do with our process. So right now we're using an off-the-shelf, fairly affordable conductive thermoplastic. For our non-conductive filament, we're using cyclic olefin copolymer, which is very biocompatible and used in a lot of medical devices already. One other thing we investigated was the biocompatibility of the conductive PLA material the microneedles are made out of. The material used for microneedles has to be biocompatible and proven to be that way before you could have human clinical trials. And while PLA is proven to be biocompatible in several medical devices, the one we're using with carbon black was not. And you can see we grew cells on the devices, right on the PLA, and on tissue culture plates beside the PLA. And you can see robust growth of the cells. We go from here, we're working on electrodeposition of nickel onto the microneedles. And the big one that we're really excited about is building our new hardware platform to produce microneedle devices. We've been working on the High-Rel Engine HR. It actually broke on us during this period, so we're looking forward to that. But there are a lot of hardware improvements. So for example, this type of nozzle is usually used on a conveyor belt. But this is one of the ways that we were able to get microneedles so tightly spaced without melding each other. And I believe as we transition this, we could possibly improve things like this even more. Additionally, we're interested in placing microneedles onto flexible electrode cables. And finally, we've been using third to fifth order polynomials to basically design the profile of our microneedle, and that kind of limits us in the complexity that we can do, and we'll be moving to spline-based CVSE profiling. Besides refining the way that we fabricate individual microneedles, we wanted to integrate this into a process to make full devices with the interconnects. And this is an example of a dual material. This is cyclical olefin copolymer with our conductive PLA, and it fits into a USB cable. The only issue is that this conductive PLA is a little less conductive than we like, ranging from 20 kiloohms to 200 kiloohms. Another place where we achieved great success, probably more than we planned, was with the post-processing script or a program that helps to put microneedles into CAD-designed devices. So now I'll briefly explain a way that we can use computer-aided design and additive manufacturing to design these devices and get the microneedles put into. The slicers, which actually translate an STL, a 3D model, into G-code, don't know what to do with the type of variable stacked extrusion that we're using to make these microneedles. So what we've done is we have microneedle markers. In this case, it's just 2 segments. These segments, though, are lines that will intersect at this point. This is where our microneedle will go. And when we have a designed device like this with balanced leads, calculations going on here to make sure these are the exact same length, therefore they're the exact same resistance, because these are our conductive interconnects. And then we've got the microneedles. We can then output this file from our CAD program to STLs, and we'll load the STLs up into Slicer. We're using Prusa Slicer. And here we assign the non-conductive material to the body, conductive material to the leads, and here's our USB connector up here at the top. And then we can assign different microneedle profiles, and this way we can actually print more than one microneedle type. Now we can go into our Python program, which spent a significant amount of time during this 6 months developing, and allows us to put not only multiple microneedles, but microneedles on multiple layers. And so we run this program, and it's going to ask us for our original G-code file. So we select that, and then it's going to ask us for the very specific G-code microneedle profiles. So we open these up, and what we can see, you can see here is a summary, total number of microneedle blocks. Those are the ones that are all the same and in the same layer, and that matches then, again, exactly with what we declared here. And this goes in and it puts the microneedle code in that so we can print it on our normal printer.
Through the Midwest Hub and this partnership with Dr. Pirlo and UD, we're able to iteratively, very rapidly develop platforms over here at UD and transition them to our lab. He can print them over here, as well as he can send a file that we can print on our, at our facilities and be able to put our sensors down and evaluate the performance as fast as possible so that we can iteratively get to the finish line.